topic helpful as you're using Couchbase Server or investigating using it for your applications. Indexing and querying is, really the key to getting your data, back to your code in the format that you need it. So it's an important topic. And before we really dig into the topic, I just want to let you know that this webinar series will continue in a couple of weeks with, another talk about cross-data center replication. So that's something that you're going to need to know about when it's time to scale up to multiple geographic regions or to have, high availability when you need to fail over from one data center to another. So come back on February 27th to learn about cross-data center replication. And, before we get into it, it's always nice to just kind of like thank the open source community that has made Couchbase possible. So we've got a lot of engineers here in-house who are working, day and night to put together Couchbase, but they wouldn't be able to do it without the community contributions, not only in contributing code for the core server and the client SDKs, but also, participating in our code review, filing bugs, helping improve the documentation, all that stuff. So, if you're one of those people, thanks to you. And if you haven't, approached Couchbase as an open source project yet, there's all sorts of resources on our website. You can go down to the footer of the website, and there's a link that says, open source, and it'll dive you right into everything you need to know to contribute. So today we're going to talk about views, which are, that's the construct we use for indexing and querying. So I'll show you a little bit of what a view is. We'll talk about the lifecycle, which is really more of a sort of deployment and production topic. We'll talk some about the, performance aspects of, having replicas and when your disk is busy doing compaction, what does it mean for your views? Then the sort of the last half of the webinar is what I think of as the fun part. It's really how do you use these views in your application to get the answers that you need. So I gave a similar webinar, a few weeks ago. This goes into more depth on some of those patterns, especially how to work with time series data. So if you were in the previous webinar, some of this may be repetition, but if you stick around toward the second half, there will be some new material. So before we really dive into views, just some basic overview. Couchbase stores JSON documents, and if you're not familiar with JSON, here's an example. It's a sort of lowest common denominator data serialization format based on JavaScript, but it has a lot in common with pretty much every programming language. I'd be hard-pressed to find a programming language that can't read and write JSON transparently. So that allows you to have documents that are all different. The database doesn't enforce a schema, so it's up to your application to decide how to store the data it wants. A big advantage of this is that as you're, evolving your application over time, you don't need to stop your development work and go administer your database to alter tables and add fields and stuff. You can just start writing new code that deals with new data, and the database will absorb that just fine. So views, which we'll talk about today, are really how you can take data that may be messy or heterogeneous or varying, where you have like the same type but different structures because it was inserted early in the life of your application versus recently. All that can be kind of normalized at index time so that when you're interacting with the data from your application, you can kind of hide the inherent messiness from your application code. The one other thing on this slide really points out that the primary data interface for Couchbase is via keys and values. So you can set a document underneath an identifier, and then you can use that identifier later to fetch the document. And there's a whole bunch of material on the web. If you look for performance-oriented architecture, you can find a blog post that I wrote about when you should balance the key value access versus the view access. So it's important kind of early on in this webinar to, point out that if what you need is sub-millisecond latency, you want to be using the key value API. And so just in a nutshell, what a lot of times will happen in an application is you will build your data structures in the database to map cleanly onto the key value API for, the most important features or, user interface aspects of your application. And then that's where the flexibility of views that we'll talk about in the second half of this webinar really kind of comes into play. Is you've stored stuff so that you can have lightning fast access to it for the hot path of your application, but you have other features in your application that need to see the data in other formats or, in other groupings. And views are great for taking this data that's kind of tightly bound to your high performance requirements and giving you other ways to interact with it. So what are views? It's the way to build an index. If you're familiar with indexes in a relational database, it's similar. The big difference being that views are native to the idea of not having a schema, so that all your records can potentially be different. So in this example, we have 3 people records that have different fields, and then the view processor is building an index that turns those into a table so that you can access the normalized form of the data via view queries. And even more than that, the real power of views lies in collating data together. So in this case, in that table, it looks like we're representing sorting things by the name key, but you could also sort things by salary or by city, depending on the lookup requirements of your application. So a view is, if you're familiar in a relational database with materialized views, this is pretty similar. We're materializing a view from the JSON documents, essentially a projection into a sorted data structure that allows you to efficiently get sequential access to documents that have been sorted near each other. So in the relational world, these terms also carry over to the document-oriented world, things like primary indexes and secondary indexes, so that you can look things up by field. But also you can do composite indexes. So for instance, you could have an index where kind of the top level of the index is the user ID, and the second level of the index is a timestamp, and therefore find activity for each user over time. And in the second half, we'll talk about aggregations. So you can write functions that are essentially, reduce over sets of the data in the view. And what that means in practice is that you can have high-speed, scalable access to, giant columns of numbers and the roll-ups you could do over them. So, a well-known drawback of, certain kinds of queries you can run on a database like MySQL is that something like a count or a sum with a group by can typically be expensive and potentially involve a full table scan or a full index scan. With Couchbase views, if you structure your view for the kind of query you're doing, arbitrary lookups across millions of rows are still happen in logarithmic time. So you can continue to get high performance even as your data set grows and grows exponentially. So some keys to the the life cycle. We'll get into this in detail in a second, but with a view, there's an indexing phase and a querying phase. And so your view definition code defines the index, and then your query parameters define the actual query that how we read from that index. So the indexes are again a little bit more big picture. In Couchbase, the actual data access to key values, as I showed in the first slide, is a strongly consistent model. That is, we favor consistency over availability within a given data center. And so you can have all your application servers hammering on a single key and not have any surprises, no stale reads, nothing like that. But the indexes are different. because they're based on the disk layer storage and updates in memory are deduplicated on the way to disk, that's great from an efficiency standpoint. You're not indexing items that are rapidly changing. But at the same time, the index will lag behind the activity in your database, by some window of time, depending on the activity in your database. For most of the use cases, until you actually get to large scale, views are going to be up to date with your main data within about a second. And you can actually, prioritize to have that be faster. We'll get into all those details in a minute, but kind of the big picture thing here is that the main data access key value path is strongly consistent, and the views are eventually consistent. So the last piece of terminology on this slide is MapReduce, and MapReduce, has a sort of a reputation for being, this behemoth that you use when you're doing large batch processing. That's not how it works in Couchbase. In Couchbase, MapReduce is a lightweight function that's used to derive the index. And so it doesn't share a whole lot of runtime characteristics with other MapReduce engines like Hadoop, although the math is similar. So let's look at the life cycle of a view, and this is especially important for DBAs and operations folks who are going to be managing performance and scalability of a cluster over time. So space up into buckets. So each bucket is a namespace, and typically a bucket is a unit of sort of administrative preferences and quotas and stuff. So with a bucket, you can set it to have a certain amount of RAM available, or you can set it to have different replica characteristics. A bucket is not how you should split up your data according to types. So it's not like a table in a relational database. It's really more of a performance and scalability unit. So within a bucket, you may have documents of all different types, of all different schemas. And then to farther break that into smaller components, there are containers for views that essentially batch the activity of generating an index. And those are called design documents. So each design document contains the view definitions for a number of views. And what's key about that from an operations standpoint is that they're all batched together to be incrementally updated. So essentially that means that the data from each document is handed to the view engine, and then each view function runs at the same time to come up with the index results for that document, and then those are persisted in the index. Grouping it like that avoids a whole bunch of overhead communicating between the database engine and the view engine. So for instance, a worst case scenario would be you've got a dozen views in a dozen design documents, and then you have 12 times more overhead associated with processing those views than you would if you just had a single design document with all the views inside that design document. Now, you've got to be pragmatic and kind of find a middle ground, because you also wouldn't want to have a design document with 100 views in it. And so typically the advice I give about how to split up the views between design documents is kind of around who owns the writing, the logic of that view. So you might have one view, or rather one design document with a collection of views that are sort of powering your end user interface, and then a second design document with the views that power the back-end administrator interface, and then perhaps a third design document with views that are used to do in-house reporting and analytics, for your developers to look at and figure out, what parts of the application need more work. So when you change a view definition, it will rebuild the index for that entire design document. And that's kind of the big reason to split the views up logically, according to which part of the code they belong to. Before we move on from this slide, there is kind of one other deployment consideration is that a design document runs over all the documents in the bucket it belongs to. And so if you have a couple of design documents, each of which only care about 1% of your data, merging those design documents is a good idea because they're generating relatively small indexes, and so you're not going to have a large index file even if you merge those. If you have, on the other hand, a design document with a dozen views, each of which indexes every single document in your bucket, that's when you might start to think about splitting it up. And then, to take that same line of thinking a little bit further, if you have some document types that you don't care about for any of your views, that you just plain don't want to index, it might make sense to stick them in their own bucket and not put any design documents in that bucket. And so then you can avoid having views running over all that data just to ignore it. So yeah, I guess the big takeaway here is that buckets and design documents really are kind of for the operations angle, to make sure that you're getting the optimal performance out of the system. So here's the data flow kind of from start to finish, which will give you a sense of what eventual consistency means in this context. So we have a document that's starting out in the application server, in your code, your .NET or your PHP code or whatever it is, and we're going to write that document via the Couchbase client libraries to Couchbase server. So the first step is the document is committed to memory on that node, and you'll get an acknowledgement back to the app server that says that happened. As soon as it's in memory on the target node, the very first thing it'll do is get scheduled for 2 outbound queues. One of those queues is to go to memory on another node, and the other queue is to write to disk. Typically, memory on the other node is going to be orders of magnitude faster than disk. So the some of the options you can have, and I won't go into detail in this webinar, but you can, as the app developer, you can ask to be notified when your document is safely committed to Replica memory, as well as waiting until it's safely committed to disk. And different applications will have different requirements, but typically you're going to get kind of as much safety going to remote memory as you will to local disk. So if performance matters in that trade-off at all for you, I recommend thinking of remote Replica memory as being sort of as important as local disk for safety and a lot faster. So now we've got this document on disk, and that's when it becomes available to the view engine. I didn't mention in this slide, but I mentioned it a moment ago, that disk write queue that that schedules the document for writes to disk is a deduplicating queue. So if you're hitting the document 100,000 times a second in the memory layer, it'll only write to disk once a second. So that helps avoid churn in the indexer as well. So now we're on disk, and the document can flow to the view engine, which can then do the calculation and update the index with the new information. So that's how it works on a single node. Now we want to look at it on multiple nodes. So here we have a 3-node cluster with 2 app servers, and the way Couchbase works is it evenly distributes your data across all the app servers, and then each database server now is responsible for building the index for its local data. So when you define a new index, and don't worry about the details of the definition, we'll look at that in the second half. That index definition is programmed into all the database servers and is used to build the local index both for the active data and optionally for the replica data. So if your application depends on view queries for really crucial stuff for the user experience, you'll probably want to enable replica views, which obviously kind of require twice the disk horsepower to manage compared to just only having active views, but it means that the view indexes are also ready to go in the case of a hot failover. So now we've got indexes on all the machines and replicas or optional replica indexes as well. So when you run a query, the query hits a random server. We tend to sort of load balance across all the available database nodes, and then that server acts as a proxy node to pull all the results together from the full cluster. So those result sets come together and are sent back to the client library. This is a constant space operation, so even if your result set has millions of rows, it's not it's not going to use a whole lot of memory on those servers. So now let's look at the defining an index phase in more detail. So I mentioned that views are really similar to indexes in a relational database. So in this case, we're building an index on the brewery documents by the city that they're in. So we want to find, for a given city, what breweries are in that city. In a relational database, you'd say create index city on the city column of the brewery table. In Couchbase, what you do is you write this function, which here in the second line of the function, if the document type is brewery, then it cares about it, and it's not going to do anything on any other types of documents. And then we want to test for the fields that we're going to use. In this case, we make sure that document also has a city field before we emit it with the emit function. So this case kind of shows an example where the view looks more complex than what you would do in a relational database. But the real power behind this approach comes when you start to have documents that may be the same type but look different. So imagine, say, a business card where everyone knows a business card when they see it, but not every business card has a fax number. Not every business card has a phone number, or maybe they'll label the phone number field differently. So you can, in the view, kind of normalize across the different ways to express that type into a single index format that's easy for your application to use. So once you've defined a view, you're going to build it. And this is, we saw that in the previous slide. It's built out on each of the database servers independently in parallel. And it builds a on-disk B-tree data structure, which is optimized for lookups by key. So I want to find all the breweries in Portland, Oregon. Or it's optimized for in-order access. So I want to find, all the comments by the user jchris in the month of March. And also, I talked a little bit about those reduces. Within that data structure lives the aggregations, which are pre-cached for, sub-segments of the ranges you can query, which is how we get the logarithmic time for aggregations even across large data sets. So I mentioned earlier that views are stored on disk and they're read from disk. And so there's, they're not as fast as the pure in-memory accesses. Hopefully, with clever application architecture, you can make up for that by using, a single view query to pull out 100 records that are all relevant. And so then your aggregate throughput is going to start to be sort of more similar to what happens from the memory layer. Now, another thing that is sort of a parallel between the way Couchbase works and the way you may be familiar with in a relational database is that views are automatically kept up to date. It's not something you have to deal with. It's just an index. Once you've defined it, it's ready for you. So it's not like a Hadoop job where you have to rerun the job periodically. Couchbase will make sure that that index reflects the state of the database, plus or minus a few seconds. So here's a picture of it, right? We run this function and we end up with a data structure. And the data structure is pre-sorted by, whatever your key is. to make key lookups and key range queries really fast. So now that we've defined the view and built the index, it's time to query it. And probably the biggest source of confusion I see from new users comes from not quite understanding the line between index building and definition and index querying. So one of the things you can't do is have access to the query information when you're building the index. And it sounds obvious this way, but when you're looking at writing a little bit of that JavaScript for the views, you might think, hey, can I figure out what the user queried on? Can the user throw an additional query option in there that my JavaScript can deal with? And the answer is no, because by the time the query happens, your JavaScript is long gone, and the index structure is what's left behind. So you're really just using that JavaScript to build an index, and then it's all about the different options for querying the index. So yeah, I've mentioned most of the performance stuff about caching reduce values inside the B-tree data structure. There's a lot of stuff online. If you really want to get database geeky about how we offer those logarithmic reduces, there's plenty of reading material for it. So you see one piece of jargon on this slide is the group level queries, and we'll show what those are later, but essentially, it's like group by in a relational database, but with perhaps a little bit more power, or at least a little bit more versatility. So we'll look at some example group level queries in the second half. So here's the basic query. We just want to find all the cities that start with the letter J. So in this case, there's Juneau. And so that's about as simple as it gets. And what will happen is your query will be reflected down to the database servers, and they'll all look to see if they have anything that matches that range. And in this case, we only have one result, so two of the servers will essentially say, I don't have anything, and one of the servers has the result you're looking for. So I mentioned this a little bit earlier, but now we're going to kind of look at the details of index building. I talked about Couchbase maintains the view indexes and keeps them up to date for you. There's some nuance to that. Essentially, Couchbase will do auto-indexing every 3 seconds, or if there are 5,000 new changes. And mostly that's a detail you shouldn't have to worry about. But if you really care about getting an exact view query to represent the state of the database you're dealing with, there are options to do that. So when you access the view, Couchbase will automatically bring it up to date also, and there's kind of 2 ways to do that. The default says, okay, Couchbase, hand me what you have now in the index, and after you've given me the result set, bring the index up to date. So that's kind of tuned to give the lowest latency and the best user experience in terms of how long it takes for the result set to come back. But if you really if you'd rather wait a couple of seconds to bring the index up to date and then run the query against the index, you can provide a query parameter stale equals false that says you're not willing to accept stale results from the view, and you'd rather have strong consistency at the expense of waiting a little bit longer for the result set. Another thing to remember is that the view data structures on disk, they're their own files, and so if you're putting large values or large keys, that's going to end up using a lot of storage. So an anti-pattern would be to omit the entire document as a value. Now you basically have 2 copies of your database on disk, and that's not very efficient. So that's why typically, and in most of the examples you'll see from Couchbase, the value part of what you can omit from the view is something small, like either a single field or a single numeric value to be used by the reducers. And if that all went too fast for you, don't worry, we're going to say it again in more detail looking at examples here. So I mentioned before, there's some different options for how stale the views can be. Stale equals update after. This is the default, and that will give you the fastest response that uses what's already available from the disk index. But the trade-off is that when you do a write and then you immediately issue a stale equals update after query, your write will not show up in that result set because you were the person who told the view to bring itself up to date, but that happens after the query. So for use cases where you really want to show the user the result of their operation, that's when you want to use stale equals false. And there's kind of even some more nuance to that, so we'll talk about that in a second. Stale equals OK is even more lenient than stale equals update after. What it says is just give me the result set from the on-disk index and don't do any updates on my account. This is the one you want to use if you have sort of a lot of view queries and a lot of writes, and you don't need exact consistency for your queries. So if you're doing something like a leaderboard that's really popular, your top 20 players or something in a game, that's when stale equals OK is best, because a user is going to be fine if it takes 20 seconds before their win shows up in the leaderboard. Now stale equals false, that's the one to use if, like, say you wanted to show a user that the blog post they'd just written is visible on their blog right after they save it. So there's a question about is update after like read uncommitted in SQL? And no, not really. It's kind of the opposite of that. It's like only read stuff that's been committed for a while. And so yeah, we can talk more about isolation levels and how how to think of them with views later. But essentially, your data item goes to memory, then it goes through the disk write queue to disk, and then the view is brought up to date. But if you are querying the view anytime in that interval, you're going to get the prior version from before that write happened. So yeah, here's a question about the query performance with increasing user load. Currently, the scatter-gather architecture that we have is, first of all, every view query has to hit every node because the data is randomly distributed. And then also, your response times are going to be only as fast as your slowest node. So that's an architectural issue that we were working on. Some other approaches, especially kind of the holy grail would be to keep an in-memory view that has anything that hasn't happened on disk yet. And so we're working out those details right now. But yeah, if you need to hammer views with a lot of traffic and you need fast responses, the best practice would be to take those results and put them in cache, put them in a memcache bucket or something, so that you have you can access them without taxing your disk systems. So I mentioned earlier there's replica indexes, and so you can when you're configuring a Couchbase bucket, you can set the number of replicas to keep. So typically people will have 1 or 2 replicas. You can have up to 3 replicas, and replicas in Couchbase are ready for hot failover. So they're somewhat resource intensive because if they're not warm, then they're not useful in the case of a failover. And the same logic applies to replica indexes, although there are more use cases where it might be an acceptable trade-off to have the index availability not be fully there in in the event of a failover, even when the data availability is still happening. So that's why it's configurable. But when you turn on replica indexes, you're going to be managing 2 or 3x the amount of disk throughput to manage keeping those hot indexes ready for failover. So yeah, this is a bucket level configuration, and it's really there for high availability. And again, that high availability constraint for views, one way to avoid getting yourself in a situation where you need replica indexes is to cache view results, in a key in memory, so that you can serve those to your end users, and that key can then provide sort of a backstop while you're waiting for the new indexes to come up to speed after a failover. So the replica indexes aren't going to be impacted by stale equals false or any of that. They're just kept up to date with the scheduled indexer. And then when you do have a failover or a rebalance, we don't actually copy over the index data structures. Instead, we rebuild the index on the new master nodes and the new replica nodes, because in the scheme of things, it's just more performant to burn some CPU to do that than to copy over the index data. So the view indexes use a similar pure tail append B-tree data structure that we also use for our core storage. And that means that as the items in the view are modified over time, it's going to take up increasingly more amounts of space on disk, and that's just a consequence of having this append-only data structure, which is really chosen for robustness. So the mitigation for having this robust data format is that occasionally it's got to be compacted. So Couchbase manages that for you. You can set a fragmentation level for the database and for the index independently, or choose a schedule to say, compact the view when it's got more than 50% wasted space, compact the database when it's got more than 40% wasted space. And there are also APIs to compact on demand. So if you have, really, if it's important to you that compaction not run at certain times, you could always manage that yourself and compact on demand. So there's another operational sort of detail that we should talk about, and that's the difference between development and production views. So a lot of our users are running big data, large clusters with millions or billions of data items. And when you have that much data, building an index takes some time. There's just a lot of bytes that have to move around, and there's no real shortcut there. But when you're just developing a view, often you want to have a rapid feedback loop between changing some code in the index definition and querying it to see if it does what you expected it to do. So what we added to Couchbase is this concept of a development view, which allows you to kind of experiment on a small subset of the data. So typically, if you're using the administration console, you'll go into the view editor and type in an index definition and click save and click query and get a result pretty much right away. And what that'll do is run on a small sliver of the data. Depending on how much data you have, it might be half of your data, or if you're really running in big data, it might be, less than 1/10 of 1% of your data. But the goal with that is, first of all, to make sure that your JavaScript evaluates successfully and doesn't have bugs in it, but also to let you, sort of see, is this the right approach for my application? Should I be sorting things by time, or should I be sorting things by, some other attribute? And often looking at the result set is really the first time you can start to see, oh, that is what I meant. So this is why the development views are there. They're there as a convenience measure. So you'll be sort of working on a view in development mode. This could happen against your production data set because the sort of those development builds are isolated and small enough that they're not going to impact production. Then when you're happy with it and you're ready to push it to production, there's a publish step. So when you click publish, what it does is, it pushes that view out to the entire cluster and gets the cluster to build it so that it's ready for querying. And there's one other kind of nicety in there. Let's say you have an existing application that's under load, and you need to, change one of the views that's in production. So you can take that design document that's in production and clone it to development mode, and then work on it in development mode and fix a bug, or add another view, or change one of the values from being null to being a numeric value, or make the kinds of changes that you're going to want to make as a developer. And then when you click publish, it takes that new definition and builds the index out completely before switching over from the old index. So you should have 0 downtime deploys, where the old index continues to be available until the new index is ready. So that concludes the section about the operational characteristics and sort of the DBA-focused interactions with the view system. And now we're going to talk about the ways that you can use this in your applications. So here's a document. It describes a beer, and it's got a brewery ID, and it's got the alcohol by volume 6.1%, along with some other information. So here's a primary index. If you just omit the meta.id, which is the sort of the second argument in the view, is this metadata that contains the ID as well as the expiration time and any flags or sort of other kind of client library level stuff that got set, you can get at it there. So the simplest index is just going to be this primary index on the ID. And if your IDs are meaningful, this may be useful to you. From a runtime perspective, it's really no different from a secondary index. Here's by name, and also the breweries. You can see we don't have a guard based on the document type in this case. And so this allows you to look up, for instance, all the breweries and beers that start with the prefix parentheses 512. Or if you just wanted to look something up directly by name, you'd be able to do it from this index. Now, this is where we start to get into kind of a more interesting secondary index. We're finding beers by brewery ID, and this is the first time we've had an example where we're using a value. So the value in this case is the alcohol by volume, and the reduce function that we're using is the built-in reduce function underscore stats. And that'll allow you to find out the average alcohol by volume across the entire data set or on a per brewery basis. So we'll look at that in a second. In this screenshot, we're showing that we have reduce turned off. So we're just looking at the underlying map phase. But if we remove this query parameter, we'll get to see what the reduce does. So we'll look at this code more closely. The value here is the brewery ID, or the key is the brewery ID, and the value is the alcohol by volume. So again, here's that result set. For each brewery ID, each beer is listed with how much alcohol it has in it. So in a second, we'll show a result where we actually kind of can look at that stuff grouped up by brewery. So here are some best practices. You want to segregate your views by their use case, as I mentioned before, so that you're not maintaining some massive index that's only used for some kind of back-end analytics every time your user wants to query something, but rather the user-facing indexes are as lightweight as possible so that you can give the best user-facing performance. Don't try and get clever in your views. A lot of people, when they start out, will write like this monster view that does everything, and over time they'll sort of get less clever and end up with a handful of views, all of which are simple. Again, it's possible to write built-in reduces. I could count on my fingers the number of times that I've seen a custom reduce that makes sense, that is really a good idea. Typically, using the built-in reduces is preferable. And then this last best practices is really key. You got to test that the attributes that you want to access exist, because if your view throws a runtime exception, it's going to prevent that document from being indexed by any of the views in that design document. Again, keep those values small. There's an include docs option that the SDKs can use to stitch the full document back in with the result set if you need that, but don't put the document in the index data structure or anything else really big. It's gonna use up all your disks. So keep the values light. So here's a little bit more sort of deployment characteristics, right? You want to, if you're CPU limited, then keep things, keep the views simple, but I think more importantly, right, be selective about what you emit, because larger indexes are going to take up, more resources, not just disk I/O, but also CPU to work with those large indexes. And a really key production factor is rebalance time. So if you have a cluster that needs to grow dynamically, and you anticipate that early on, you may want to turn off the replica indexes, or you may want to disable the index-aware rebalance, because index-aware rebalance, tries to keep that consistent snapshot happening even while data is flowing to the new node in the cluster, and that can increases a lot the amount of work, logically that's required to maintain that correctness, and as a result, it becomes, a fair amount slower. If your rebalances are something that, you're not in a hurry to get finished, there's nothing wrong with having a rebalance that takes 24 hours. The system will be stable during that kind of operation. So, but if you're impatient to get to the larger capacity, then you may want to turn that off and sacrifice some consistency during the rebalance. You need to have spare memory available in order to use the, to get the best performance out of it. So you can't dedicate all your memory to your caching layer. You need to have some memory that looks idle that the file system cache can use. And more file system cache is going to make your queries much faster and, of course, give you more throughput, because you've got a disk system that's dealing with data items as well as indexes, and the more file system cache you have, the more of those blocks are already in memory for the view reads. So let's get back to that view with the alcohol by volume. Here you can see we've turned group equals true back on, and we're reducing. And so we're reducing grouped by brewery ID, and thus we're getting the statistics for each brewery. The brewery IDs are kind of opaque, but you could use them to look up the brewery description document and figure out, exactly which brewery it is that has, an average alcohol by volume of 5.8%. And, the important thing about this view is it lets you know which brewery can get you the drunkest by taking the sum and dividing it by the count to find the average. And again, this is just using that built-in stats reduce. The underscore count reduce and underscore sum reduce, those are both subsets of the stats reduce, essentially. So the stats reduce tells you the count and the sum, as well as some other information that is useful for finding things like the standard deviation. So when we group, what it does is it's essentially grouped by brewery ID. So this is giving you that roll-up per unique brewery. You could also turn group off, and it would give you the roll-up across the entire data set. So you could figure out across your entire data set what is the average alcohol by volume. So there's a really popular pattern in our MapReduces for dealing with timestamps. So, well, it's behind this purple box, but the timestamp here is just a string format. It looks like we took it from an old SQL dump. It's not a special format. Our view indexers are capable of dealing with messy timestamps. So, it's good. It's a good practice to make it so that your timestamps collate in alphabetical order, having that be the same as time order, but it's not strictly necessary because you can normalize your timestamps in the JavaScript view definitions. And we have a helper function here that allows you to do that without a whole lot of heavy lifting. So in this case, we are counting items that were updated, and we're segmenting that over time. So in this case, we can see, some months are much more popular than others as far as when these items are updated. And we'll drill in here and look at this helper function. So built into the JavaScript runtime is date2array, which takes a field out of your document and converts it into something that looks like this, where the time segments are split into a numeric JavaScript array. So 1970, February 18th, 5 p.m. and 42 minutes and 51 seconds. And that allows you to do group levels on this one index. So you've got one on-disk data structure that can give you roll-ups on a yearly basis, a monthly basis, a daily basis, an hourly basis, and even all the way down to the second. So the date2array is pretty powerful in that it'll take integer-based timestamps, epoch time, string-based timestamps, anything that the sort of built-in JavaScript date parse can handle is acceptable input. And then the output is going to be this array. And it's also got, safety checks and stuff. So if you pass it something that is undefined or a string that is just not a date, it will return null. So you don't have to do a whole bunch of type checking before you call date2array. So with group level 2, we're segmenting by month, but with group level 3, we would segment by day, and it's really handy for getting these kind of graphs. So you have a single underlying index that allows you to drill into data, and it's great for analytics type user experience. Another great pattern, really popular, right, is a leaderboard. Finding the top rated beers in this case, or you could find the players, who have the most wins. And so in this case, we've stuck the ratings onto the beer document itself, and what we want to do is find the average rating for each beer and use that. So this doesn't even use a reduce function. It's as simple as building the average up inside the map function and emitting it as the key. So we can find that the Honey Pilsner has the top rated beer here, and there's more below that. So this allows you to do a single lookup to display a leaderboard to your end users. So that's kind of it for slides here. I'm happy to take questions, and I'm also happy to take feedback offline if you want to reach me that way. So yeah, thanks everybody for attending, and I hope this was helpful for you. If you could think of any ways this webinar could be better, don't hesitate to let us know. That's what we're here for. Oh, it looks like we have a question coming in. Oh, so the presentation should be posted in the next couple of days. We'll send out an email to the registration list so you can't miss it. Oh, this is a great question about pagination. So I didn't cover it in the webinar, but we do have some resources in our documentation and on the blog about pagination. The gist of it is that you don't want to do page-style pagination. There's no efficient way to jump to page 200. It's linked list-style pagination. So at the bottom of a page, it's easy to link to the next page. If you want to deeply link within a result set, then you're going to need to use like a natural key, whatever your key is. So link to the blog posts from April rather than link to 200 blog posts ago. So yeah, I think that's all we have time for. Again, contact me online if you have more questions, and thanks for joining.